Okay, so thank you for the invitation, first of all. And uh, I was kind of deciding what to present today. I've been working on one aspect of my research the last few years has been on causal inference. And this is not my newest work, but I think there's quite a lot in there to discuss that is interesting to kind of include in a talk that's to a more general audience. So I'm going to talk about some work that I've been doing with my PhD student, Elena Yozova, who is finishing her PhD, but she already has a teaching lectureship here at UCL, and a former visiting PhD student called Nathan McJames. And ultimately, at the end of this talk, we're going to talk about combining data with and without unobserved confounding. But the bulk of the talk will be a little bit about causal inference and heterogeneous treatment effect, and trying to convey some of the intuition and also some of the technical challenges and what it really means to be doing causal inference and heterogeneous treatment effect modeling. So what's heterogeneous treatment effects? The first thing is, I know most people have heard of the term causal inference, and in causal inference, we're trying to understand how a factor affects an outcome, all other things being equal. Okay, so if we're talking about the medical treatment, if two patients are exactly the same and one gets the treatment and the other one doesn't, what do we expect the treatment effect to be? Of course, the best way to go about this is to have some kind of randomized experiment, an experiment where we get to choose who we give the treatment to and who we don't give the treatment to, because it makes it easier to make comparisons. In reality, we can't completely randomize everything. Randomized control studies tend to be limited. They're small, they're expensive. It's hard to make sure you follow up all your patients quite closely. So often we try to get some information from a randomized study, but also then to see what's happening in a larger study that is observational. And observational means, first of all, that we don't get to choose who gets the treatment, but also may mean other things like the measurements are not consistent in the same way. The criteria for entering the study might be slightly different. So observational study, the main thing that one thinks about is how you assign treatment, but they have other differences as well. Now, causal inference in the traditional sense talks about an average treatment effect. And more specifically, there are lots of models out there, especially in the older literature, that say, if you get the treatment, you will get better by X, for example. So there is a constant treatment effect that is, for example, a constant offset in a linear regression, in the simplest case. Things have changed a little bit, that there are lots of the literature talks about average treatment effect. So the effect might not be the same for everyone, but we care about the average. But in the last decade or so, there's a lot more focus on, we don't care about learning just the average. We want to understand how the treatment effect varies as a factor of your characteristics. So we want to be able to make decisions to say what will be the effect of treatment on this particular patient who has these characteristics. Okay, so in general, and this is what I'm going to talk about in a minute, all of these problems are regression problems, ultimately, in the sense that we have some data, we have some X's that we can measure, we're trying to predict some outcome. The outcome could be risk of death, it could be some numerical measurement, I don't know, blood pressure, but fundamentally, in the crux of it, there is a regression model. And that regression model, in some way, because we're going to have a lot of covariates coming in some way, we need to apply some shrinkage. And shrinkage means that we don't want to have a very complicated model, because we'll end up having a model that is overfitting. In other words, it's trying to learn too closely my current data set and would not generalize well to other data sets. And the difficulty of doing this in the context of causal inference is that the thing we're trying to learn, which is the effect of treatment, is something that we never get to see, because we will only ever see somebody with or without treatment. We can't observe both things, okay? In some sense, you can think of this as a missing data model, that you're trying to model two possible outcomes, but you can only ever see one. Okay, so today's question that we will get to later, let me check the time to check we have later, is if we have data sets, if we have a data set that's clean and it's randomized, and another data set that's much larger, but it's flawed, should we combine them? And if so, how can we combine them? And how can we make sure we don't actually contaminate the information that we have from the good data set, as it were? It's not a very technical talk mathematically. I think some things are a little bit subtle. But so let me go through these kind of main concepts. There's three main variables here. Y is my outcome. You could think about blood pressure. Z is a binary treatment. It could be 0 or 1. There's a lot of work going into non-binary treatment, for example, dosage, but I'm not going to talk about that today. And X is a vector of covariates. So these are things that affect what my outcome might be if I'm a patient. They also might affect whether I get the treatment to begin with. In all of this work, we are using what's called Rubin's causal model, where essentially we treat the two possible outcomes for each patient as, in a way, as a missing data problem. We're saying everybody has two possible outcomes, treated and untreated, but we only ever get to observe one of them. The Rubin causal model is not the only way to do causal inference. It's also not always necessarily the best way, but it's one of the simplest if you want to use regression modeling. So this is what we're going to do here. And the quantity that we want to estimate is the conditional average treatment effect. And this means as a function of X, so for a patient with a particular patient profile Xi, what is the conditional expectation of the difference between the two outcomes with and without treatment? Now, there is an important distinction here, and if you've not seen causal inference before, this will take a moment to differentiate in your head. Here, talking about with and without treatment, it means I take a patient, Xi, and I'm going to randomly give them treatment or just not give them treatment and subtract the expectation of these two values. That is not the same as looking at the expectation of Y conditionally on treatment, because the treatment decisions are made depending on patient characteristics. So that is not the same as saying, I will randomly intervene and give you or not give you treatment. If you condition on treatment having been assigned, and we don't know how that treatment decision was made, then this is a different distribution. And I will give you an example later. So conditional average treatment effect looks at this expectation, the conditional expectation, which is the difference between treated and the treating versus not treating a particular patient. It's essentially the difference between two functions of X, right? If you want to think about it mathematically, this is an expectation, so there is no distribution here. This is just the difference of two functions. The average treatment effect is taking expectations of this difference over some distribution of X. So if you have a population, imagine that in some way we had a very good model for this difference. Depending on the population profile you're looking at, you would take expectation over a different distribution of X, right? And this is, in a way, it also is an aspect of generalizability and transportability. If we have results, for example, from a clinical study in one country, we can't just go to another country and apply it because the profile, the patient profile characteristics might look quite different. So you would have to take expectations over your relevant distribution. So here is an example, and it's a toy example that I made. I coded it up. It's not real data. Real data is never quite this clean. But imagine the following. Imagine that we only have one patient characteristic, and it's my covariate X. And we have one response, which is continuous. And we have people who were treated and people who were untreated. So on the left-hand side, I have generated this figure in the following way. I'm saying, first of all, every patient X has two potential outcomes. So this person here is the same person here. And only one of these 2 points is ever observed. So here, if this is a blue one, the other one is going to be gray. So it means if I observe the possibility of the outcome, if that patient is treated, then I don't see the treatment. Okay, so that's essentially what this plot is showing us here. Blue means treated, red means untreated. What else have I done here? I've said that the higher your covariate X is, the more likely you are to be treated. So how do you see this from this plot? Well, you can see that there's a lot more blue up here, whereas down here, most of the points are essentially down in the untreated, group. Okay, what else do we observe here? The untreated response in general increases linearly, whereas in the treatment group, it's a bit of a mess. It goes up and down. Can't remember what I put in there as a nonlinear function, but it's clearly not linear. What's the nice thing? Even though, so the first one, the most naive thing somebody could do would be to take the average response of the blue and subtract the average response of the red. This would not be a good idea because you have given the treatment to many more of the people with the high X's than vice versa. So you really first need to condition on X before you do anything else. But the good thing is that I've created this figure in such a way that we can actually model the probability that each patient was observed as treated or untreated, because we have the X that is relevant here, and we have the Y. So this is a case of what's called observed confounding. It means that there's a variable in there, my X, which affects whether I will be allocated treatment, and it will affect my outcome, but I can measure it. So I can model it in some way that will allow me to kind of try to estimate the difference between these 2 dashed curves. So the dashed curves here are the 2 means, my mu1 of X that I mentioned in the previous slide and my mu0. Okay, now when are things bad? Things are bad when I have unobserved confounding. So when the allocation to treatment is affected by something else that I don't get to see. So what I've done in the right-hand side plot is that I've created an additional correlation. I've said for every point for every pair of points that I generate, so the potential outcomes treated and untreated, if the treated potential outcome is high, I'm going to automatically allocate that patient to untreated. So what happens now? Now, if you imagine that I haven't seen any of the gray points over here, if I were to just fit a curve through my blue points, what would happen? I would be underestimating because I can't see any of the gray points. So if we have unobserved confounding, essentially, there's no way out. There is no way to know that this information is missing unless I have external, expertise to tell me, no, this is actually bad. You can't do this because we know how the data were collected and they were not collected in the way that you want, essentially. So there is unobserved confounding. The nice thing about observed confounding is, imagine asymptotically, nothing that I do is asymptotic, but it's important to talk about asymptotics. If I were to let the number of observations go to infinity here, I could learn the blue, I could just completely separate the blue and the red, fit some nonlinear model through the blue, fit some model through the red, and subtract them, and everybody would be happy. There's no problem as such. In the observed confounding, if I let the number of blue points go to infinity, I will always end up underestimating because I'm always going to be more likely to observe the lower points than the higher. Okay. What I'm going to kind of build towards in this talk is situations where you have both types of data and you're trying to say, if I have both types, if I have one data set that has only observed confounding and I can use it in a reliable way, and I have some other data with unobserved confounding potentially, should I just throw out this data set, or is there a way to combine it with this one to borrow some information? That's essentially the context here. Okay, so how do people do heterogeneous treatment effect estimation? The first thing is that there is a few kind of standard assumptions. The first one is that there's no interference, so my treatment will not affect your outcome. If you imagine for many things, this might be the case, but if you think about households, this might not be the case. If I change my diet, then my family's diet will probably also change, right? So it depends a little bit on how micro your study is. Consistency means that there is no multiple or latent version of treatment. If you give one treatment, you expect to have one outcome. It could be a distribution of outcomes, but there's only one version of treatment. And unconfoundedness it's a question mark, right? In the previous plot that I showed you on the left, this was unconfounded, which also is called observed confounding. You can also call it observed unconfounded or observed confounding, kind of, you can treat them in the same way. So this means conditionally on X, there is no correlation between the treatment and the outcome. So in the previous plot, if I know my X, I can model directly the probability that somebody's assigned treatment versus untreatment, and I can separately then model the outcomes. Whereas in this case, conditionally, if you know that somebody has been allocated to treatment for some value of X, you still know that there is some correlation between that allocation to treatment and the value of Y. Well, I only know it because I've created this plot, because actually you're more likely to be biased to have observed a smaller value. The bad thing with this assumption is there's no way to test it. Unless you have external information, it's an untestable assumption. So the only thing you can do is, if you have a reliable data set that you know is unconfounded, maybe you can use that either as some kind of grounding or some kind of testing to say, should we just discard the other data set? Can we combine them? The final assumption is overlap, which says that for any value of X, so for any value of your covariates, we need there to be non-zero probability for a patient to fall into treatment versus control. So if we look here, if I'd had a region over here that had no reds whatsoever, it had all been gray, that would be a region of poor overlap, which makes sense, right? If I didn't have any red points here, and my whole aim is to learn the difference between these two average curves, well, anything that I do here with the red is extrapolating. I have no idea. So overlap is another assumption. It's an important assumption, but the good thing is that if it's violated, you can see it because you can look at the data, or you can, estimate this probability. Okay, so how do we define the conditional average treatment effect? As I mentioned, this is defined as the expectation of the difference between treated and untreated conditionally on X. Now, if this unconfoundedness assumption holds, in other words, if the treated and untreated outcomes are independent of the allocation of treatment conditionally on X, then this expectation is actually equal to the expectation of Y conditionally on treatment minus conditionally untreated. And then what does this mean? This means that we can now use conditional regression, right? We can use any kind of regression method we want to try to model this, right? But it's important to highlight this distinction. This is only true if we assume that conditionally on X, these outcomes and Z are independent. So we can instead condition on Z. So let's say that we could condition on Z. Then what is this? This is just a difference between two expectations. There's a million, types of supervised learning or type of regression models that you could use. In general, all of these models use some generalization of the following form. We say that Y, my outcome, is some function of the covariates and the treatment plus some error. Quite often the error is normal. Doesn't have to be. You could have something more complicated. You could have that your two outcomes, Y1 and Y0, are correlated in some Gaussian process space. There are lots of options, but fundamentally, essentially, what you're trying to do is build a regression model that will map you from X and Z to Y in some way. Different models that are out there, and we had one of my first papers in causal inference was my former PhD student, Alberto Caron. He wrote this review paper where he tried to read all the different papers in the literature that do this in different ways and categorize them. So for each of these papers, they differ in two ways. One is, what kind of regression model is used in the background? Is it a linear model? Well, is it a linear model? Is it random forests? Is it neural nets? Is it Gaussian processes? Is it some kind of spline? People have their own favorite regression methods that they use. And the more important aspect is, how is treatment embedded in that regression model? And I will show you what I mean in 1 second. If you imagine that, so you could imagine doing this in two ways. One might be that I write down some model where Z, my treatment, is just another covariate, right? So I have some nonlinear model, blah, 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 and then maybe I have an additive term that is added only when people are treated, say. In this case, this would work quite badly because the effect of treatment is very nonlinear and it's very non-constant. So treating the treatment as just another covariate works well when the shape of the treated and untreated is quite similar. And you can think of it either, it doesn't necessarily have to be constant. Maybe they model it as a linear function, but essentially you're going to have a lot of borrowing of information between the treated and untreated, which might work well. It wouldn't work well in my toy example here. The other extreme would be that you're saying, I think my treated and my untreated are completely different. I'm going to model them completely separately, fit a regression model for the red, fit a regression model for the blue, and be done with it. Asymptotically, this is the best thing you can do, but we're not in asymptopia. So we want to at least borrow some information between the two, because people, it's unrealistic in real life that this is what happens. There's going to be some information borrowing in terms of what the treatment effect is across patients. Okay, and the next thing to reiterate is, how do we think about, in that regression model, embedding this problematic data set on the right? Okay, Bayesian Causal Forests. So a long time ago, in 1988, Robinson wrote down quite a basic expression of causal inference in the following way. He said, well, we can write down the outcome as some baseline. Forget about this pi hat for a moment. We can say that the outcome is some baseline, which can be a function of x, plus the treatment effect as a function of x times 0, 1 of treated or untreated, plus some error. At first sight, this seems like an approximation, or that you are creating this additive, you're assuming additivity. That's actually not what's going on here. Treatment effect, the conditional average treatment effect, by definition is additive. If I had said that my conditional average treatment effect is actually the ratio of y1 divided by y0, then this parameterization over here would no longer be, just by definition, okay? But because by definition, I've expressed the treatment effect to be additive, I can always write the outcome as some baseline as a function of x, plus some function of x treatment effect times z. Of course, yes, what you do with the error here, there are different options, but fundamentally this parameterization is due to the additive nature of the conditional average treatment effect. Okay, so Han et al. So the Bayesian Causal Forests is a paper that came out in 2020 that used this parameterization to use nonlinear regression to do causal inference. And the main punchline of the paper is the following. If we think about medical studies, for example, the medical context, the most informative thing, let's say that you have two patients. One has come in with pneumonia No, you have two patients. They've come into the hospital with pneumonia, and you're trying to think what's going to happen about whether you get this treatment versus no treatment. The biggest information here is not going to be the treatment, but it's going to be the age of the patient. If one patient is 20 and the other person is 90, the other person is 90, that information is going to be a lot more predictive of the outcome than whether you use this or that treatment. So what does this mean in a regression context? It means that the predictive effect of your covariates in terms of your baseline is very, very strong for predicting your outcome, even if you don't know the treatment. So if you put everything into a regression model, and treatment effect is just another thing that you have in your model, it is very easy for the model to, for example, over smooth and completely lose the effect of treatment. What does this mean? It means that we need to have some way of penalizing overfitting, but we also need to have a way to tell the model that I actually do explicitly really want to understand what the effect of treatment is. And it's not so clear how you would do this in a regression model, because most regression models optimize prediction of the outcome. But that's not here. My aim here is not just to predict the outcome, it's to be able to say, what is the treatment effect? What of that outcome, how much is the effect of one versus the other treatment? Different methods achieve this in different ways. Well, some methods don't achieve this, but there are several methods that achieve this in different ways. The BCF model does the following thing. It fits a nonlinear additive regression tree for the prognostic, so this baseline prognostic effect, and a separate one for the treatment effect. And what it means is when you fit this model simultaneously, you can have a prognostic baseline effect here, which is very rich and very predictive. But then you can separately try to pick up a treatment effect that might not have such strong signal. So this parameterization is quite nice. I think it separates things quite nicely. And we also had some work with Alberto still that said this allows us to also manually pick out which covariates are particularly informative for the baseline and which covariates are particularly important for the treatment effect. For example, it could be that age is very, very informative of outcome, but the treatment effect doesn't depend on age. Whether you're 85 or 25, this antibiotic will shorten your, I don't know, the length of your illness by 2 days. I don't know. Okay. The other thing that they did in BCF is that they modeled, I mentioned earlier, because we can see the covariates and we can see who's treated and who's untreated, we can directly model this, it's called a propensity score, this probability of treating versus not treating. You can compute, can estimate these propensity scores, and you can also put them into your model as a way to try to capture this kind of predictive, what's the word? Anticipatory confounding. So what I mean by this is, in general, you have a patient coming in. You're going to, if you're not in a randomized experiment, you would decide what treatment to allocate depending on how you think the patient will respond. And what this means is that there's going to be a lot of correlation between outcome and treatment, and you can try to capture some of that by sticking your prognostic effect into your propensity score and your prognostic effect. Okay, another way to think about this is you can think about your baseline as a nonlinear intercept, and you can think of the treatment effect as a nonlinear slope of the treatment itself. But in any case, these are called different things. This can be called prognostic effect. It can be called baseline effect. This is called treatment effect. Okay, I am needing to speed up. In BCF, they use the regression trees to model this. What do regression trees do? A single regression tree takes, imagine you have your covariates in some space. You pretend that it's bounded, essentially, and then you start introducing binary split rules across different covariates. You might split here, and you continue. And then you could say, for example, that within each element of this partition, the distribution of the outcome will be normal with a constant mean and some variance. Now, a single regression tree is not great, partly because these are very these result in very unsmooth objects, essentially distributions. And because if you want to search the whole space of trees, it is computationally very expensive, because to get from this tree to a tree that looks quite different, you would have to cut your tree all the way back to explore the space of trees. So instead, what people do is they try to model the response variable as the sum of many of these trees, like 100, for example, plus some error. And the nice thing about this is that each tree is what's called a weak learner. So each tree describes a little bit of the variability of the outcome, but together these trees give you something that is much smoother. It can capture quite rich patterns of response, and they are easier to explore in the space of regression forests. Because if you go to try to change one of the trees, that single tree doesn't explain that much of the variability. So it's easier to change it without completely messing up the predictability of your model. And if you assume that the errors are Gaussian, which you can argue is or isn't sensible, then the computation is easy. Okay, so now we get to what Elena and Nathan and I have been doing. Back to that plot that I showed you. We have one data set that only has observed confounding, and we know how to model it. And we have one data set which may have unobserved confounding. It's a lot bigger. This is what happens in reality. It is a lot bigger. But it also doesn't necessarily have the same distribution of covariates. So you might have to qualify for a clinical trial. You need to fulfill some narrow criteria. If you're talking about observational data, it's a much wider range of distribution of covariates. And the question is, what can we do about combining these data sets? Okay, so the reality might look a little bit like this. We have an experimental data set where, you can see here the X ranges from like -3 to +3. The observational data have a much wider range. It's a much bigger data set, and it has this unobserved confounding. So the question is, if we could get a rough estimate of the curve here, of the blue curve, and a rough estimate of the red curve, could we use these rough estimates within a joint model to try to extract something useful about the blue data? Yeah, about the observational data, and vice versa. Can we combine these in any meaningful way? Now I will show you an example of what I meant earlier about unobserved confounding. This is a very, very toy example of how unobserved confounding works. Imagine that we have a very simple additive process. My y is some f of x plus additive some g of u plus the treatment effect times z plus some error. The point here is that u is unobserved. If the u is not correlated with anything else, this doesn't matter. What would happen in reality is that it would get absorbed into the error. If I don't observe u, then it would get absorbed into the error. Potentially, I would have to have a more flexible error distribution, but it would be absorbed into the error. Now, what happens if my u is unobserved, but it's also correlated with z? Well, let's go back to my estimand. It's the expectation of y if I've intervened to allocate treatment minus y if I've intervened to say untreated conditionally on x. My question is this the same as the conditional distribution? Like I mentioned earlier. So I said if we have conditional distributions, we can use regression in whatever way we like and everything is fine. Can we use regression here? Well, what's the problem? If we look at the corresponding conditional distributions, and for clarity here, I've added the index, the subscript here. We're taking expectations over y conditionally on x and z, of y conditionally on x and z is equal to 1 minus z is equal to 0. Let's look at this first blue term. What is this expectation? This expectation, well, we don't know it because we know the formula we have for y here involves u, and we need to integrate out u. So it's the expectation of y given x, z is equal to 1. I should have had a u here as well, of y given x, z, and u, and then take expectations over u given x and z. Now we can, if this is easy to compute, we're going to have f of x, right? This doesn't depend on u, and it doesn't depend on z. Plus, well, this term tau of x, again, is not a problem. If we condition here on z is equal to 1, then this is tau of x, and then we take out expectation over u is not a problem. The term that's causing a problem is this one, because the expectation of u conditionally on z is equal to 1 is something, but the corresponding term, when I try to expand this one, will be slightly different because u and z are correlated, so they will not cancel out. When I subtract this from the corresponding conditionally z is equal to 0, the f's will cancel, that's nice. The tau will stick out, that's nice, that's what I want. But the expectation of u conditionally of z being equal to 1 versus 0 will not cancel out. So this conditional distribution is actually different to the one I want, and that's what's going on in that example I've created. This is essentially what this says. So when you try to subtract these two conditional expectations, you end up with a bias, which is the difference in expectations of g of u conditionally on z is equal to 1 versus 0. And that's not equal to the conditional average treatment effect. So how can we address this in BCF? What we did in this case is we said, okay, well, let's assume there is one, some original true model that I want to capture. But I will assume that my first data set, the data come from this correct model, but in my second data set, the observational data, there is potentially a bias term, both in the prognostic effect and in the treatment effect. And what are we going to try to do? We want to, in some way, penalize the model to say, if the two data sets, for some values of x, if they are in agreement, then we are happy to say, look, the observational data agree with the randomized data, so let's go ahead and increase our confidence. But if we're in a region of x where it looks like they are quite different, then we want the model to say, oh, no, hang on, I think my observational data actually is really off, and I'm going to go and assume that there are large values of mu2 of this bias in the observational data. So what we want to do is we want to penalize. We don't want to use this extra bias term if it's not needed. If there are regions of X covariate space where there is agreement between the data sets, then we'll say, no, they're actually in agreement. There is no problem. Let's just go ahead and say the observational data can just be directly thrown into the mu1 that I'm trying to learn, and vice versa. Now, what happens when we do this? What ends up happening is when you're fitting a model, essentially, you can imagine you have a likelihood. It's not a complicated likelihood, but there is some likelihood here. And you have some terms coming from the observational data and some terms coming in from the experimental data. You can even imagine as a function of x, because we're using trees, you're in some region, some element of your partition where everything is constant, and you have let's say, 10 points that fall in that element of your partition. What could happen in there? If you have 1 point coming from your experimental data and 9 from your observational, what happens is that observational data will completely drown out any sensible information coming from your experimental data. So we need to be really careful in how we decide whether to say, oh, I think they're in agreement, right? If the experimental data only have 1 observation versus 9, then you can say, whatever, maybe the model doesn't know. The model doesn't know that we're trying to say, look, really trust that experimental data. Don't get carried away by the observational, because that's not so reliable. And The way that we did this is the following. We used, so this, you can imagine this is your standard model where you have some priors about your parameters, and then you have a big likelihood. Many of the points in the likelihood come from the data set that's reliable, that only has observed confounding. And some of the terms in your likelihood come from the part of your data that may have unobserved confounding. And what happens with any model, if you're combining two data sets, when one is much bigger than the other, the bigger data set will tend to really dominate what ends up happening with your parameters. So we wanted to have a way to say, look, don't overdo it, especially if you're in regions of covariate space where you really don't have a lot of the good data. You mostly only have bad data. And the way that we did this, I won't go into the details, is for each value of X, essentially, we try to say, if you're in an element of the partition, for example, where you have one good data point and 9 bad, we are going to dampen the weight of the information. So the weight of the likelihood of the bad data by 1/9, essentially, roughly, such that the flow of information is actually the same between the good and the bad data. And that means that throughout the whole covariate space, you have the same level of contamination potentially from the two data sets. And that is you can tweak whether you want that to be 50-50 or 20-80 or whatever you want to do, such that it gives you some level of confidence and control over whether you're over-contaminating or under-contaminating. We've tried many different things. You can also try a constant. You can try different things. I don't need to. I'm not going to go through the details, but what I will show you is here's an example that it's kind of a toy example, but it follows the same principles that I mentioned, that we have some unobserved confounder. We have a W. And then we have covariate distributions for observed and unobserved confounded data sets. So one is much narrower than the other. And we're going to fit a model that depends, in the case of the unobserved confounding, the probability of treated versus untreated depends not only on X, but also on this unobserved variable U. And then we have an outcome that depends on U, depends on this W that is just a nuisance, but it's harmless, and X and U. So what happens here? Here I'm showing for each of different options of the model, this is the root mean squared error of doing the following. This is fitting BCF, so the original model, assuming that you can see all the unobserved confounding. So as if both of your data sets were perfect. So this, in a way, is a benchmark. This is what would happen if you combine the two data sets, but ignored the fact that there could be unobserved confounding. And then these 4 plots are showing you what would happen if you try to dampen that likelihood in different ways. So eta is equal to 0 means that you're essentially only taking your good data. Eta is equal to 1 means that you're considering, you're taking all of the data, but knowing that there could be an offset. Adaptive eta does what I mentioned down here, that it tries to balance that the flow of information between good and bad data is the same. And it looks like this adaptive eta is not doing very much, but when it actually starts becoming quite visible is in regions. If you look at the region of covariate space where I have quite a lot of good data and bad data, then it's not making a big difference. And why is that? That's because I already have quite a lot of good data. So it is able to come through. But as I move away from that, as I move away from the regions where I have a lot of good data, that's where the danger zone appears. That's when it starts looking like you're introducing bias by taking more of your contaminated data. And that's what ends up happening here, that if you use this adaptive eta, the difference starts appearing, the benefit appears when you look outside the region where you have an abundance of the unbiased data. Okay, I'll wrap up because I know I'm a minute over time. the point is that when you're doing causal inference, essentially, all you're trying to do is model a conditional distribution. And having unobserved confounding means that the conditional distribution that you want and the one that you have are different. And how you build that into a regression model and how you try to borrow information across can be tricky and I don't want to say unpredictable because it is what it is, but it needs care. And there's a lot more that needs to be done here because, for example, what if we had two data sets that didn't have all the same covariates or had missingness or had complex confounders? But that's in another PhD, I think. I'm going to stop here and have some reference.